Hi everyone. In today's video, we're going to talk about training with different precisions in JAX. We're going to look into vision transformer implementation. So let's get started. So these are different options to control the precisions in JAX: dtype, parameters type, and precision. You can find all these options in different layers in flax. So this is the linear layer in flax. Here's the dtype and the parameters type and the precision. We're going to play with these options and see how this will affect the memory and running time in TensorBoard. So I'm using Kaggle notebooks. Here I'm importing the libraries and I'm setting data configuration and model configuration. These two functions will convert the CIFAR10 images into NumPy arrays, which makes them compatible with JAX. I'm using grain data loader to load the images into a train loader, and I'm setting a device mesh 8 by 1, so I'm splitting the patch images across 8 devices. And this is the regular vision transform architecture. I actually did not optimize this for the loss or accuracy on CIFAR10, and the sole purpose was just to play with data types and see how this will affect the memory and running time. So this is the badge embedding class, which has a convolutional layer that cuts the images into patches, and an encoder block which has the attention block and the MLP block. So you notice here that I'm using nnx with partitioning. This is not applicable in our case because we are not using model parallelism. We're only using data parallelism. So this will not affect the layers, the parameters, but I'm just keeping those just in case if we change the parallelism configuration here. The first thing I've done is to print nnx.tabulate. So nnx.tabulate is a function that prints all the parameters with their data types and their dimensions, and you just send a dummy tensor with the same dimensions and it will print all the parameters into the model. But one important thing to note here is that you have to turn off all these nnx with partitioning. So these should be commented out to run nnx.tabulate. So this is nnx.tabulate. I run it and I got this output. So the input is float 32, 1 by 32 by 32 by 3, and the output is 1 of 10 classes, and it will be bfloat 60. This is the input and output for patch embedding, and this is the parameter. So when I run nnx.tabulate with different parameters type, I set it to float 32, float 16, and bfloat 16, and these two are almost half of float 32. So running with the parameters type bfloat 16 was a no-brainer actually. So it was an easy decision. But when I run the vision transformer with that, I got this XLA runtime error. So it wasn't expecting the parameters to be bfloat 16. And this explains why the parameters are actually by default set to float 32. This is something inside XLA just for accumulation and matrix multiplication. So this cannot be touched. That's why I'm commenting this out here. So this we cannot control that. Now let's try different data types for dtype. So this one here, we're going to set it to bfloat 60 and float 32. And I'm trying different batch sizes. So this is the peak memory allocation in TensorBoard. For batch size 128, I'm getting the same for both precisions. But for batch size 4096, I'm getting more memory. I was curious why there is no difference between float 32 and bfloat 16 when the batch size was 128, but there is a big difference, almost a gig, when we increase the batch size to 4096. What makes sense to me is that there should be a small difference here that got expanded when we increase the batch size. So I had to dig more and go to a TensorBoard. So this is a profile for float 32 batch 4096. If I search for 32 by 32 by 3, this is the original dimension for CIFAR10, and this is the first convolutional layer. Notice that the input is 16 by 32 by 32 by 3. 16 is actually 128 divided by 8, it's 16, but it's a bfloat 16. There was another operation that copied the float 32 tensor to bfloat 16 tensor. But when I change the batch size to 4096, I don't have this conversion. So the input is still float 32. I don't know what causes this. I don't know why XLA is passing the tensor as float 32 if the batch size is 4096, and it's passing the tensor as bfloat 16 if the batch size is 128. If it's the batch size that controls this process, is it an internal heuristics for XLA? Is it I'm doing something wrong? I don't know actually. But I tried to minimize the error. I removed everything, and these two profile files are for the patch embedding only. This convolutional layer, I removed everything and kept this convolutional layer and run it for a single step, and I still find this conversion happens when the batch size is 128, but it doesn't happen if the batch size is 4096. So apparently this data type is just a hint for the compiler to use bfloat16 or float32. But the compiler does not always respect this. It has other calculations to do. It has to do with the memory, with the batch size. There is another option to control the precision in JAX. It's called jax.lax.Precision. So you can pass it in a linear layer. You can pass it here as jax.lax.Precision.highest. So in the documentation, they're saying default is the fastest, but the least accurate. High performs float32 computations at 3B float16 passes. Highest, it's the slowest, but the most accurate, performs float32 computations in 6B float16. So this is the difference between those, and this is the default. Sometimes it's called default, sometimes it's called fastest, but I got an error with fastest. Maybe they changed the code, but I kept it as default. I tried these different options, the default, the high, and the highest. I was expecting some difference in the running time. So with different batch sizes, I just got the same running time. I'm actually measuring, so in TensorBoard, for highest, I'm measuring the average step time, which was 6,400 milliseconds. And for the default, I'm getting 6,400. I couldn't have an impact on the running time or the memory using this option. And the final option to control the precision in JAX is jax.default matmul precision. You just wrap the training loop with this line. So you can choose pfloat16 or float32, and this will control the matrix multiplication inside the training loop and certain precision. But I didn't notice any difference in the memory or in the running time. Yeah, so the only difference I made was in memory when I increased the batch size to 4096 and I used float32 instead of pfloat16. So bfloat used less memory than float32, but in other cases I couldn't make an impact on the memory or the running time by controlling the precision. And there are multiple reasons for that. The first reason that I could be doing something wrong, which is always possible. And the second reason is that XLA always has the final say on precision. So they have their own heuristics to control the precision, and because this is these are very low level commands, and they are leaving the user with the choice of how many devices and the batch size, how large is the tensor that he's trying to pass to XLA. So I think XLA has more control on the precision, and it has its own heuristics to set which precision based on certain inputs, the batch size, which is the tensor size, and the number of devices and the memory load. So it calculates all these inputs, all these parameters, and it makes final decision. For the user is just giving hints to the compiler, but the compiler does not always respect that. So I recommend that you just reduce the batch size or just play with the batch size and keep the input tensor to pfloat16, and you just measure the TensorBoard and you just watch for any potential out of memory errors. That's it guys for today's video. I hope it was helpful. I'll share a link to this blog post in the description below. Thanks for watching. Bye.